this video, we're building towards trying to integrate with spherical coordinates, and so of course we're going to need the volume differential for spherical coordinates, right? So remember that anytime that we integrate, we partition a region. In this case, it's a 3D region that we partition into these little spherical boxes. And then we sample a point in that spherical box, that's the function value, and then we add everything up and take the limit. Well, we need to figure out the volume of one of these spherical boxes. So that's going to be our volume differential. So before we get there, I just want to review how we get the length of an arc of a circle, because that's going to come into play in our formula. So here is this little pizza slice where the angle between the two radii is theta, and then we have the radius r, and we want to know an expression for the arc length of L of that little sector. So I'm going to form a ratio of full circle to wedge, right? So the length of the full circle is its circumference. That's 2 pi r. And I'm going to make that, well, that is related to an entire rotation around the circle, which has 2 pi radians. And that has to be in proportion as the length of our wedge, which I'm going to call L, and our angle theta. So I just have a proportion here that tells me that from full circle to a full circle circumference to the full circle's angle, that ratio has to be the same as the length, the piece of our circumference of our sector, of our wedge, divided by the angle of our little wedge, right? So this proportion must hold true. And so we're going to solve for L. We can see here that 2 pi's cancel, so that length L is just going to be the radius times theta. That's how we get that little arc length L. And we're going to use this below when we try to figure out the volume of a small spherical box. All right, so let's move down, and we have a little spherical wedge here, and we've got to figure out its volume. So let me label, the green axis is the y-axis, the red axis is the x-axis, and the blue is the z-axis. And this is angle theta on the xy plane. So that little wedge on the xy plane, we're going to just call this a little d theta, a very small change in theta. And this arc right here, that arc length right there, well, we know that the radius is r from the origin to here. So we can describe that little piece as r times d theta, right? So it's the arc length that comes from a little change in theta. And notice that that's going to give us one of the sides of our little spherical box. So that side length is going to be the radius on the xy plane times a little change in theta. So that's going to be an important dimension that we're going to use. Notice also that the horizontal ones right here and here, those are caused by a little change in phi. So, right, this is angle phi, and we change it by a little bit. Let's call that little change d phi. And so we want to know, what is the arc length of one of these pieces, right? And when the boxes become arbitrarily small, I only need one of these lengths. So let's take that one. And that's going to be the radius. This time the radius is rho, right? All the way out, that's going to be rho times our little change in phi. And I'm using the idea that we developed earlier, that one of these little arc lengths is radius times angle cut. And then finally, the missing one that we have, this length in our little spherical wedge, that's going to be a change in rho, right? So that's just going to be a little d rho, little change in the radius. So we've got a little box whose dimensions are change in rho times change in phi, that comes from a little arc length caused by phi, and r times change in theta caused by a little change in the angle theta. So let's go down below, and to get the volume of that little wedge, of course, I'm assuming it's a very tiny little wedge. To get the volume of that little wedge, we're going to call that a little dv, very, very infinitesimally small volume, where again, the change in rho is very, very, very tiny. And so that's going to be r times our little change in theta. We also have rho times a little change in phi, and then we also have a change in rho. So we're very close to getting our volume differential. The only problem is that we have an r here that's not one of our spherical coordinates. But we do know how to relate r to phi and rho. So one of our conversion elements is that r is rho times the sine of phi. And you can look back at the first introduction of spherical coordinates if you want to look at where this comes from. But r is rho sine phi. So now we have that our volume element that comes from multiplying kind of the three sides of this little spherical box is going to be rho sine phi times d theta, right? That's this piece, times rho d phi times d rho, little change in the radius. So that's going to be, well, let's write our rows in the front. We have a rho squared sine phi, and our differentials will be d rho, d phi, d theta. I'm writing it in this order because we're always going to have a rho simple surface. So this kind of will be the order that we use in integrating with spherical coordinates. So we're going to start rho simple, then theta simple, then phi simple, then theta. So this is our volume element. And in the next video, we're going to start with our first example and write down a triple integral in spherical coordinates.